Welcome back. So in this video, we're going to talk about elastic and inelastic collisions. So we introduced the concept of collisions and in particular concept of momentum being conserved in the previous video. And I'll put up a link up above there. And what we want to be able to do now is to distinguish. So there's two kind of key collisions that we discuss, especially in the early on stages of talking about momentum. Now, I will keep the examples one-dimensional and the discussion one-dimensional, but this, of course, can stem out into 2 dimensions and 3 dimensions, and not just with 2 masses or 2 objects colliding, but in multiple objects colliding. So first off, let's begin with the elastic collisions. Most of the time when elastic collisions will be discussed, they're going to be called perfectly elastic collisions. It is unnecessary for us to call them perfect because when we are discussing elastic collisions, we are actually referring to the concept of the fact that both momentum is conserved and kinetic energy is also conserved. Now, we are assuming that there's no external forces being added into the system because then if there is a net external force, then obviously even momentum, okay, as you have it, because your velocities will be changing. So here, the only change that happens is due to the collision between the 2 objects, okay, that we have, or more objects for that matter. Now, momentum was discussed, so here's the equation. So in terms of a déjà vu, it is dependent on vectors, but when it is one-dimensional, then typically those vectors will either become positive or negative, where you take one side, so for example, going to the right being positive, to the left being negative, or up being positive and down being negative. Kinetic energy, which is a concept that you should have studied now a little while back. I'll put up a link up above there to kinetic energy. And what this states is whatever object that you have, so if you are dealing with, let's say, 2 objects, and those particular 2 objects, so here I'm referring to them as M1 and M2, I'll draw them as just simply circular balls for the moment. So we have something of this nature. And if I call this M1 and then this one M2, and they go in and they'll have and collide, well, before the collision, what they will have is they're going to have a certain amount of kinetic energy. So right here, this is the amount of kinetic energy that they would have, both of these, before the collision. So the little I just stands again for the initial, all right? And initial means just how much do they have initially. And then the second component on the right-hand side, this means how much kinetic energy did they have afterwards. That, of course, also applies to momentum. So on the left, you have initial, so before the collision. And then on the right, you have momentum, which is right after the collision. So if these 2 particular objects are moving, okay, so towards each other, so they'll have a certain amount of velocity or speed in that case. So let's imagine that this one is v. So this is the speed of the first one initially, and then this one would be the speed of the second one initially. Of course, the speed could also be 0, so that means one of them is not moving. You can't have both of them 0 because then there's not going to be a collision at all. So that's how we were going to define these. Now, because they are vectors, we can certainly put these little arrows, okay? So the vector symbols right above them, and that's what you see right here in the momentum equation. So again, elastic collisions create the concept that both momentum is conserved and also kinetic energy is conserved. And that only happens in elastic collisions. Now, the second component, which is inelastic collisions, momentum is conserved. Now, momentum is always conserved, so that always sticks around. And also, the total amount of energy is always conserved. However, in inelastic collisions, that total amount of energy doesn't necessarily stay in kinetic energy. And that is due to the fact that, for instance, it can transfer. So as it is pointing out right here, that can transform into heat, into sound, into even deformations, right, of the object themselves. So hence the word inelastic. So this holds, so the amount of momentum that you have, again, assuming that there is no external forces being added into the system. And this okay, is equal to before and after, meaning momentum. But kinetic energy is not conserved in this case. So we don't typically will use the amount of kinetic energy that we have. So those are inelastic collisions. Perfectly inelastic collisions, which I am writing right here. The word perfect means it's a very special case. So it is an inelastic collision. So momentum is conserved. So here, notice right here, here's our equation. But you'll notice that something interesting happens in this equation, that on the right-hand side, in terms of your final velocity that you have, we have combined both object M1 and M2, which means that after the collision occurs, they stick to each other. So they're kind of stuck together after the collision. And that's what it is, or at least that's what we are referring to with the word perfect. So the two objects, so one of them could be stationary or both of them could be moving, and then they collide. And then when they collide, they will stick together. So for instance, if you have two vehicles and sometimes they'll have it bumper to bumper and they'll actually get stuck together. And now they're creating one body which is moving in exactly the same speed. Now, if that doesn't happen, so if they do bounce back in some form or way where the speeds are a little bit different, then that is an inelastic collision, and that's not called a perfectly inelastic collision. Please don't forget, momentum is always conserved in any closed system without external forces being added. Of course, all right? So we cannot keep adding extra forces, because if that happens, then the net external force is actually not zero within it. The kinetic energy is only conserved in elastic collisions, or sometimes called perfectly elastic collisions. But the total energy, just like the total momentum that we have, is always conserved, but not necessarily in the kinetic energy. It can go in many other forms in terms of energy, so it can transform into that. Here's the perfectly elastic collision. And again, so here, this word is really unnecessary, but it does happen in textbooks, okay, that it does pop up. So I'll just say elastic collision for the moment. So we have a ball of mass 1 kilogram and it is moving at 4 meters per second. It collides head-on with a ball of mass at 3 kilograms initially at rest. Find the final velocities of the two balls after the collision, assuming no external forces are present. So this is before the actual collision. All right, so magic. So we can actually go ahead and try to calculate these out overall. So we have all of these givens. So here's M1. Here's that first particular speed. Here's the second one. And this one they're saying is at rest. Now it would not actually matter if it was at rest or not. We could certainly just substitute it back in if it was necessary. Just keep in mind that if they're going in opposite directions, you would have had a negative symbol in there. All right, so for the momentum, so that's right there, we will have 1 multiplied by 4. The second one is 0. All right, so this is plus 0. So that is right there. So this would have been kilograms, meters second. So check, that's just before, that's on the momentum side. Now in terms of the kinetic energy, right here, so we can calculate that in as well. So we can substitute that in. 8 joules in total amount of kinetic energy. Now afterwards, so the final velocities that we want to be able to find out, which is the right-hand side of the equation. Okay, so that's something that we're going to try to now substitute as well. All right, so if I have this, so this is before, right there. Now I want to be able to find out what that was afterwards, right? Now I do not know in here, because this is something that I have to find out. So I know the masses, but I don't actually know what these two particular velocities were right there, okay, that I have in here. And of course, I don't know them in here as well. So if I do that, so I'm going to do that right here. I know is going to be equal to 4. All right, and that is coming from right here. Okay, so this is after, and this is before. Now, if you put it on the left or on the right, it doesn't matter. I'm just taking this entire thing and then equating the two sides. So that gives me one equation right there. So this equation would give me 1, okay, F. I'm going to actually do this. I'm going to say 4 minus 3 V2F right there. Now the second one, in terms of the kinetic energy, okay, so that I will have, okay, so that I can take a look and substitute that entire thing as well. So that's the total amount of kinetic energy afterwards, and this is supposed to be equal to 8, okay, which is what it started. So because it is a perfectly elastic collision, then these two must be conserved. So within here, so notice I can certainly get rid of the 2. Okay, so this 2, I can multiply both sides, and this is going to be 16. This will be V1F squared plus 3 V2F squared. And now I have a second equation. So what do you do here? Right? This is definitely not a linear equation because it has the square, so it's a quadratic of some form. It is in 2 variables, but notice that I can substitute this into this equation. So after a little bit of algebra, I actually just put this in here because we're squaring it, just in case you want to see where that goes. All right, so then I substitute it back in. All right, so I square this, and this is what we get after the massaging. That's from right here. And then I am taking out, so notice the 16 and 16 cancels. Okay, so this is what I'm going to get. And now we have to solve for V2F, and look what happens. So within here, so I can take out the 12 V2F from right here. So I'm going to get V2F minus 2 is equal to 0. Okay, so this is what I have there. And I'm going to get, okay, so this is V2F is equal to 0. So that's one solution. And then another solution, so this is just a quadratic. That means that V2F is equal to 2. And this would be in meters per second. And this is meters per second. All right. Now, so your second one that you had, so you started at 0. Okay, so this is where this is kind of coming from right there, but we certainly are not going to end up with that. So this is going to be our solution. All right. Now you can, certainly think about this, right? You can say, oh, how do you know that it's definitely not 0? Well, if you go back and you substitute 0 into here, so notice if I go back to the original, okay, what I substituted, so let me take that back. I just want to convince you here, because sometimes as a student you may not know, like, why are you not considering 0? Because it has 2 solutions. Well, that solution of 0 is the initial one, because if you now took this and substituted 0 into here, you would have gotten 4. So right there, so V1F equal to now 4. All right, so that would have given you one of the solutions that you would have had. And so one would have been basically not moving, and then the other one continues to move. And here, so if you think about it logically, now this one was at rest. Okay, so what we're saying is this will remain at rest after the collision, right? So as you're going to be colliding it in, okay, and notice that it started off with 4 meters per second, okay, and then this one was at 0 meters per second from the start. So if those are your solutions, those are just your initial, so before the collision, that's what you're getting. So this is what you started off with, which is not your final after the collision happens. So after the collision happens, it's going to be the second one right here. So this is 2 meters per second. And what does this mean? So this is positive in here, so this ball, and that should make sense to you if one of them is moving towards it, and then you have the other one which is stuck. So this will hit it, and it will move in collision. So this is going to hit, and this one's most likely going to bounce back, just depending on how much mass it has. So one is in the positive direction to the right. And now if you do substitute that in here, what you're going to get is 4 minus 3 times 2 and this is 4 minus 6, which is going to be equal to negative 2 meters per second. Okay, or in other words, it is moving at 2 meters per second, so it bounces back off, so it loses some of its velocity, and it goes in this direction. So here's the first one, and then here's the second one. My apologies. Here's the second. Okay, so that's the second mass, which goes in this direction, and then here's the first mass, okay, which goes in the opposite direction. So the sign just tells you that when you're dealing with one dimensions. Now, you, of course, may not start with 0 in these examples. This example starts with at rest, but that does not matter. It would have been exactly the same procedure. So you set up your two equations, you isolate, you substitute, you're going to run into a quadratic, then you can solve the quadratic, or you can plot it. You can use something like decimals within, although on a test or quiz you won't be able to do that. So within here you should know how to substitute and then deal with quadratics. So that's the first example with an elastic collision where we can find out what the final velocities are. So there we go. We have those are final velocities right here and right here. So check. Here's the second example that I have for you. And this one is perfectly inelastic collision. And in a perfectly inelastic collision, what do we know? That kinetic energy is not conserved. So we can't use that particular concept where the kinetic energy before is equal to the kinetic energy afterwards. Now, perfectly inelastic means that the two objects get stuck together. So let's see here what happens. So it says a girl of a mass 40 kilogram runs and has a speed of 3 meters per second and then jumps onto a stationary swing of mass 10 kilograms. Find the maximum height the girl reaches on the swing. Okay, so this is a really neat example. So let's imagine we have a swing. All right, so I'm going to have a swing like this. And here's the seat of the swing. Here is my girl. My apologies. It's going to be a stick man, okay, or stick girl. So there we go. So the girl is running along. All right, and so there we go. So this is what's happening. The girl runs along and then jumps onto the swing and then holds on, right? So we have the mass. So this is 40 kilograms for the girl. We know that she is running, so 3 meters per second. So there you go. Jumps on the swing itself, has a mass of 10 kilograms. And here it says it's stationary, so this is at 0 meters per second initially. So the information that they're asking us for is they want to know, now of course, if you jump on the swing, then this is going to start to swing, right? It's going to swing upwards, assuming that it's not breaking, right? So this is going to now swing kind of like this, all right? So it's going to go, I'm going to try, okay, good, worked out perfectly. Okay, so there we go. And then that swing, we want to know how high it gets to. So we want to know what that height is right there. So it goes right, okay, above there. So let's call that height H with the girl on the swing. So how do you, approach this? What are you going to do about all of this whole concept? So in order to be able to solve this, well, we know that when the girl jumps on, the swing and the girl are going to move. So they're going to have together a certain amount of velocity, right? So that would be like saying mass of the girl plus the mass of the swing. Those are stuck together and they're going to have a certain amount of speed. Now, when they have a certain amount of speed, they do have kinetic energy. So right after the collision, they'll have a certain amount of kinetic energy. Now you might say, well, the kinetic energy, I thought it doesn't get conserved. No, it doesn't get conserved, but you still have kinetic energy if you're moving. So that kinetic energy we know is 1/2 the total mass, which would have been the mass of the girl plus the mass of the swing, and then your total final squared. That's the total amount of kinetic energy that you would have right after the collision, if it's even if it is inelastic. So this holds true. Now we have these, but we don't have this, right? Or at least don't have it yet, but we can certainly find it. Now you might be saying, well, okay, so why do you need that? How does that have to do? I have to find h, which is the height. Well, we're assuming that all of this kinetic energy now, again, this is, a perfect system. And again, this is, a high school or first year type of problem, right? Of course, there's frictions and other things, but then, even momentum starts to get hairy. So we're assuming that's an ideal system where this total amount of energy afterwards, right? This is going to swing, and it's going to swing to a certain height. So it's going to have a peak. So this is going to peak at something. Now, at that peak, it no longer has any kinetic energy. So here what we're using is the law of conservation of energy, where we're saying all the kinetic energy is going to go into the gravitational potential energy, which is your total mass. All right, so that's the mass of the girl and the swing, multiplied by gravity times height. That's what we are doing. So we're trying to say all the kinetic energy is going to transfer at the peak to the gravitational potential energy, which would have been the maximum amount of height that you have. And all we need to know what that speed is. But that speed we can obtain from the conservation of momentum. Even though it's an inelastic collision, they get stuck together. Remember, momentum gets conserved as we're again assuming that there's no external forces. So here, I am going to go back into my law of momentum equation. And here's that equation where what we're going to do here, so this is our swing. I'm going to call V2 our swing. Now this is 0 because the swing initially is not moving, so it's stationary. So that's what we'll have here. This is our girl who is running along, I forget, so 3 meters per second. So that's what we have there. And now notice, so mass 1 plus mass 2. So mass of the girl plus mass of the swing. So 40 plus 10, which is 50. And that's a pretty easy equation now in order to be able to check what that is. Now again, I'm just dropping the vector symbol because we know that it's going to just move in one direction. If the girl's running in this way, then both the girl and the swing are going to continue in that direction. So here, this would be 120 is equal to 50 VF. You can certainly find out. So this is 120 divided by 50. And so within there, so 5, and that should be 1, 2, so that's what, 2.4 meters per second. And now once I have this, then I can now substitute it all into here. So this is what I'm going to be dealing with. That is going to be our equation, and the masses will always cancel in these perfect systems that we have if we are going back and forth between kinetic and gravitational potential energy. So now I can certainly solve for h. So h is going to be 2.4 squared divided by 2 times 9.8. So that's just moving this on the other side, and we can certainly do this relatively quickly. So that would have been our height. Now you can round it to whatever significant figures you want. We pretty much just had 1, so we can certainly round it to 0.3. But my goal was to try to explain to you how this concept works. So that's it. Okay, so thanks for watching. We'll see you in a future video. Bye, everybody.